Example the first. Find the area of the region bounded by f of x is equal to x squared minus 2x on the interval from 0 to 3. My recommendation is that we start by drawing a graph of this thing. Here, let's draw some axes. And to graph this parabola, I'm going to suggest that we factor it. So there is a common factor of x here. Let's pull it out. X times x minus 2. So we can do this with the intercept method. We've got two intercepts, 0 and 2. Boom, boom, boom. Yeah, that should be good. Let's throw in some x-intercepts here. 0 and at 2. In our parabola, let's see, it's a referee pointing upwards, so perhaps it looks something like that. Wow, it's as if it's computer generated. It's so perfect. Okay, and then we are going up to 3 here. Okay, so you can see sort of a problem because we said that our function has to be non-negative. It's supposed to be up above the x-axis, and if we stretch from 0 to 3, we've got stuff that's down below and we've got stuff that's up above it. Well, you know what? Let's just see what happens when we find the limit of a Riemann sum for this particular example. And so what if our function is somewhat down below the x-axis? Should be interesting. Okay, so to start this process off, we do need some rectangular widths, which we'll call delta x. We'll use the regular partition formula. 3 minus 0 over n gives me 3 over n. That's the width of each one of our rectangles. And in our picture, let's just sketch a few of these things, right? And I might just draw a handful of them in there using the right endpoint because that'll be far easier. But we know that there's going to be, we want ultimately there to be like an infinite number of them, right? So here's a couple of them. And then maybe like right there's another one, joop, 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 joop. And maybe over here I've got another one. What perfect rectangles you're drawing. And then maybe, dang it, and maybe over here, here's another one. Okay, again, we can see that there's some down below. We see that there's some up above. Now let's use this width that we came up with as 3 over n. That would be where I'm going to evaluate the first the height of the first rectangle. This is a 3 over n. So I'd want to find f of 3 over n, right? And then I would want two widths for the next one. It's going to make this 6 over n. So I'd find f of 6 over n. The next one I'd want three widths. 9 over n. F of 9 over n, and so on. All right, but we want to kind of generalize that because we want it as a function that we can plug into our Riemann sum here that we're going to take the limit of. So realize that this f of 3 over n is supposed to be what we get when we plug in I equals 1. And when I plug in I equals 2, I'm supposed to get f of 6 over n and I over 3 for 9 over n. Okay? And maybe it's obvious to you that this is just, if I stick in 1, I'm supposed to get 3. Stick in 2, I'm supposed to get 6. If I stick in 3, I'm supposed to get 9. Those are just multiples of 3. This is 3i over n, right? Again, if I stick in a 1 here, 3 times 1 gives me a 3 over n. If I stick in a 2, 3 times 2 gives me the 6 over n. If I stick in a 3, 3 times 3 gives me my 9 over n, and so on. All right, so I think that we're in business. So our heights will be given to us by a function value like this, f of 3i over n. Okay? All right, let's put it all together. Let's find the limit of the Riemann sum. See what happens when part of our function is down below. We want the limit as in the number of rectangles goes to infinity. Here's a question for you. As the number of rectangles goes to infinity, how big do they get? Or should I say, how small do they get? All right, we need our Riemann sum. There's our limit. Riemann sum is from I equals 1 to n of, and then the product here is our heights, f of 3i over n, times our widths, our delta x, which we said was just simply 3 over n. Boom. Okay, recall that the variable for the limit is n, but the variable for the summation is I. So this 3 over n is a constant with regards to the summation, so it gets to come out. But it gets to come out right here and not outside of the limit because n is the variable with regards to the limit. So let's rewrite here. 3 over n times our summation, and I'm going to get totally lazy here and not keep writing this upper and lower bounds. And now I want f of 3I over n. I'm going to plug that into the function. F of x was equal to x squared minus 2x, I think. Yup. So let's see. I want to plug in a 3I over n. I want to square that guy. Minus 2 times 3I over n. All right. It's looking good. Now let's simplify some more. Learn to write the word lim. Pulled it off. N goes to infinity. Bring this down. Summation 9I squared over n squared minus, that would be a 6I over n. Okay, and then what I would do is remember that I just want the sum of the I squared and I want the sum of the I. All the rest of these things are just going to be constants that we can pull out. But when we pull it out, we're going to have to use some brackets. Like so. 3 over n, boop, 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 bracket, and then I'm going to pull out this 9 over n squared out of the first summation. And this one is going to be the summation of the squared integers minus, and then we'll pull out the 6 over n from the second one. And this was just going to be the sum of the integers. Close those brackets so nobody gets upset. And now we will use our little formulas that we totally have memorized for the sum of our squared integers and our integers, like so. What is this? It's a mess is what that is. This is what I'm talking about. Man, if there was only a way to write this down much, much simpler so I don't have to keep writing all of this garbage, and it is garbage. It's not garbage. I'm just kidding. I'm just playing. Let's see. 9 over n squared. The sum of I squared, if I remember correctly, is n times n plus 1 times 2n plus 1 over 6. Verify that if you will. And then minus 6 over n. The sum of I, that's the Gauss one, which is n plus 1 over 2. Right? Let's continue to simplify. Eventually, we're going to hit some calculus. 3 over n, cancellation crayon. Cancel out one of these factors of n. Cancel out a common factor of 3. It's going to be a 2 there, a 3 there. That should be good. A 3, n plus 1, 2n plus 1 over 2n. Minus, let's cancel out some stuff. Oh, it's so satisfying here. Oh, that gets a 3. And a 3n plus 1. You can expand these things out if you want to. Oh, I don't need this bottom because everything canceled out. Now distribute your 3 over n to both of these terms. And eventually, 30 minutes later, we will be done with this single problem. And we haven't even really started the lesson. I mean, this is almost a warm-up question. Top times top gives me a 9n plus 1, a 2n plus 1 still, over 2n squared. Yeah, minus a 9n plus 1 over just an n. Now I think we're ready to take the limit of all of these pieces, and by all I mean both. Why do I have like a closed parenthesis but not an open one? Fixed. Okay, let's think about this. When we plug in infinity, of course, this would be infinity over infinity, but these are super easy rational functions that we can just use pre-cal rule in order to evaluate the limits. Leading coefficient here, if we were to like FOIL this out, this would be a 2n squared, but we're multiplying it times the 9 that's out front, so it's really a 18n squared. The n squared over the n squared, so those degrees are the same, is going to be 18 over 2. So that limit is just 9. right? You could write it as 18 over 2 if you want to, but it simplifies down to 9. And then finally, the leading coefficient here just be a 9 times n here. So it's 9n over n. N's would cancel out, giving me just also 9 for a total of 0? What? We did all that work and we just got 0 as our final answer? What the heck happened? So this, of course, is what happens, well, it's what could happen when part of your function's down below. So the only way that that's possible, of course, is if this piece is taken to be signed as positive, and we must have subtract off a piece down here, so this is going to be signed as negative. And that's how we interpret it when our function is non-negative. You don't really say negative area. I know that's usually how we vocalize it, but negative area doesn't make sense. It's area with a negative sign in front of it, signed negative. So let's kind of summarize that right about here. It's all about net area. Riemann sum, our function f, we can see some pink functions here. They're real pretty. We have some area underneath a curve with this kind of tan color, which is less pretty. On the left-hand side, this is a Riemann sum because we've broken it up into rectangles. If we find the area of all of those rectangles, basically the Riemann sum there, I don't get the area under the curve. I get the approximation of the area underneath the curve, right? It's not quite the exact one yet. How do I move from this one to that one? I have to take the limit as n approaches infinity, and then I will get the exact area underneath the curve up above the x-axis, right? That's what happens whenever our function is non-negative, up above the x-axis. But if it is not necessarily entirely non-negative, we're going to say that anything that is up above is going to have a positive sign in front of it. Anything down below is going to have a negative sign. And so sometimes they cancel out. Not exactly always. You could have a net area which has a negative sign. You can have a net area which has a positive sign. Over here on the left-hand side, we still have an approximation. So this is a Riemann sum of a function in which it is not entirely non-negative. We're going to say that this is the net area. Up above is positive, down below is negative, so some of these areas are going to cancel out. And one more time, in order to move from the picture from the left over to the picture at the right, I just need to take the limit of that Riemann sum to get the exact net area bound by our function and the x-axis, where anything that's down below is signed negative, canceling out with anything that is up above. Now, don't get the wrong impression that these things are always going to equal 0. No, like I said, it just depends. Where do you have more area? Do you have more area up above, or do you have more area down below? If you have more area up above, of course, your final answer is going to be some sort of positive area. And then if you have more down below, your net area is going to be overall a negative number.